The Smith chart allows us to plot impedances, and impedances in general, Z, have a real part, which is the resistance, plus J times an imaginary part, which is the reactance. Let's do an example. We take a series combination of a resistor of 100 ohms in series with a capacitor of 100 picofarads. So the resistance is 100. The reactance for a capacitor is minus 1 over 2 pi F times C. So we need a value of frequency to use in this calculation. And I chose a frequency of 15.915 megahertz. In order to get a value which would be interesting for our reactance. The capacitor value is 100 picofarads. So we'll do this calculation. I'll work out the denominator. 2 times pi times 15.915 exponent 6 times 100 exponent 12 minus equals, then I take the reciprocal to give me 100. So the reactance is minus 100 ohms. On the Smith chart, we plot normalized values of impedance. The center is labeled 1. I have a Smith chart which is in color. It doesn't show up so well on the camera, but the red 1 is 1.0 is right where the circle is. This is the bullseye, the dead center. This is represents our system impedance. Our typical system impedance resistance value of 50 ohms. So I normalize by dividing through by 50. So 100 divided by 50 minus J, another 100 divided by 50 gives 2 minus J2. So we're looking for the intersection of a resistance of 2 with a reactance of minus 2. The resistance is located on these circles where this point, which corresponds to a resistance of infinity, and by the way, this point here corresponds to a resistance of 0. This is a resistance of 1. So I'm looking at circles. Which go around this path. Again, the circle's labeled in red. So here is the circle labeled 2. So I will highlight that with the pencil. Then in the upper hemisphere, we have positive values of reactance, which would correspond to inductor values of reactance. And on the lower half, we have negative reactance due to capacitors. So we're looking for minus 2. Now the reactance curves are arcs. They're actually part of a circle, which we only see part of, but here's an arc, here's another arc, and so on. So I'm looking for the arc labeled negative 2, which is, let's see, -1 is right here. So this arc represents the reactance, -2, and the intersection of the arc and the circle is my impedance for this series combination of resistor and capacitor. Now, as a circuit, this could look like this. This is my 100 ohm resistor in series with a 100 picofarad capacitor. This ground plane PC board is an isolation by gluing in here a little disc punched out from another PC board. And I'm going to use a nano VNA to measure on a Smith chart like this, and to show its correspondence with this point. So here's the nano VNA. And see if we can get it so that it's more visible. Lower this a bit. The first thing I like to do is get rid of all these extra traces. So I tap here on menu and it says display and trace. So if I click on the trace, I can make it disappear. The blue trace, make it disappear. The green. I'm left with this pink trace, which would be fine. I'll go back. I'm doing an S11 measurement, which means that the signal will be leaving the zero port, or sometimes labeled port number 1, the output port, and then it's reflected off of our circuit and it comes back. And it's a measurement made with that reflection and a reference signal, which will provide us information for the Smith chart. So I'll click this and select Smith. So now we see our Smith chart superimposed. The next thing to do is to set the frequency range of interest. So I have 15.915. So I'm going to go from 15.8 to 16 megahertz. That's somewhat arbitrary. So let's see, we'll go back, and select stimulus, start, and select 15.8, 15.8 M for megahertz. And that shows up here as a start frequency. Now to set the stop frequency, I'm going to select the 16 megahertz, 16 M for megahertz, and that shows up here. Now that I have the range of frequencies to sweep over, I'm going to calibrate the nano VNA. Go back, select calibrate, click calibrate, and then it asks for open, short, and load. There's one additional calibration called through, which would be used if I were using both the output and the input ports 1 and 2. But in this measurement, I just need the short, open, and load. So the open is the first one that is suggested. So this is an open calibration termination. Screw this on here. By the way, good idea to acquire or buy some male-female adapters SMA so that you can screw them on in the event that these fragile connectors become bunged up, strip threaded. You just have to replace this adapter that you added on and not have to worry about getting into the nano VNA and repairing it. So I just added the open. I'm going to click open. Next one will be the short. Short circuit. If you look at it, there is just a complete continuous connection between the center pin and the case. So that's our short. So loosely tighten that on, click short, and then load. Load is a 50 ohm load. It's provided with the nano VNA. That's this termination connector here, connection. I'll attach that. Click load. Click done. And I'll save it here. It seems to be empty. You can now verify that the calibration is working. This is the 50 ohm load, and we see that the marker is right at the center. When I remove the 50 ohm load calibration termination, I essentially have an open circuit. So there's the infinity point. I could connect the open, but it's not necessary for this check. And now I'm connecting the short, and you see that the short goes to the zero resistance. So this horizontal line is pure resistance. The center is at 1, corresponding to 50 ohms. All the way to the right is infinity, and 0 ohms short circuit is at the left. So again, do the calibration first, set the frequency range, and then do the calibration. So now I'm going to connect my circuit. And we have excellent agreement with what was predicted before on the Smith chart for the location of the intersection. Also, we can read that this is for the value at 16 megahertz, and that the value is 418 minus J408. You can play with the cursor adjustment location to put the frequency closer to 5.915. That's the value of frequency I had selected in order to get to 5.916, because I can get in order to get to a reactance value of 100 ohms. And we see that we have 420 and minus 409 as our values.